Hi, I'm Ranjit, and in this video, I'll be talking about a convex hull algorithm. So before I write any code, I'll briefly talk about what a convex hull is and how our algorithm is going to work. So imagine you have a collection of points in a plane. So that's the collection of points. Now, imagine these points are nails, like, you know, on a surface, and imagine taking a rubber band and stretching it out to fit all of these points and letting go of the rubber band. The shape that rubber band would take, that is the convex hull for this set of points. It is the smallest polygon that is strictly convex while still containing all of these points. That's the convex hull. So how do we calculate that polygon given a set of points? That's what the algorithm that I'm going to explain, that's what that algorithm is going to do. So the first step in our algorithm is to take this list of points and sort it based on the x coordinates of the point. So considering the x and y axis to be like so, if we sort this list of points based on the x coordinate, this would be the first point and the index 0 point, and this would be index 1, 2, 3, 6, 7, 8, and 9. So once we sorted our list of points, we're going to iterate through this list and start adding these points to our polygon. So first we take point 0 and add it to our polygon. Then we add point 1. Now that we have 2 points, we have an edge pointing in that direction, edge 0, 1. Then we move on to point 2 and add it to our polygon. So now that we have 2 edges, what we want to do is to make sure that the turn between every 2 edges is always a right turn. So the turn between edge 0, 1 and edge 1, 2, you can see that it's clearly a right turn. So we don't have a problem with that. That's a valid turn. So we continue to point 3. Now, this turn between edge 1, 2 and 2, 3 is a left turn. So that's a problem. So whenever we see a turn that's not a right turn, we delete the vertex at which that turn is happening. So in this case, we delete point 2. So when we do that, we end up with an edge directly from 1 to 3. So this is the process. We keep iterating through the list, making sure all the turns are only right turns, and whenever we see a left turn, we delete that point. So I'm going to quickly apply that algorithm and go through the rest of the points. So point 4, that's a left turn, so we delete 3 from our list. Then point 5, point 6, left turn again. So that, and then point 7, sorry, that's a left turn, so delete that. Point 8, left turn, delete. Point 8 and point 9. So now we've reached the end of the list. So we continue doing the same thing, but we move from the end of the list back to the beginning of the list again. So from 9 we go to 8, but 8 is already inside our polygon, so we skip it. And then we go to 7 next. So that's a right turn. That's okay. Then 6. Oh, that's a left turn, so we delete 7. Then to 5. That's a right turn. That's fine. 4 is already inside our polygon, so we ignore it. We move to 3. That's a left turn, so we delete 5. Then point 2, left turn again, so we delete 3. And then next is 0.1, but it's already in our polygon, so we ignore it. And then 0.0. So that polygon is the convex hull for that set of points. So that's how the algorithm works. So now I'm going to try and demonstrate that with that Python script for Rhino. So before we start writing any code, let's just create a random set of points. Oops. Okay, so that's our random collection of points. Okay, so just import Rhino script syntax first. And this will be the main logic of our script. First thing we're going to do is get a list of points from the user. So our message will be select points. And we're going to use a filter for point. So that's going to give us a list of points. Now we have to calculate a convex hull for that set of points. So I'm going to write that algorithm in a separate method. I'm going to call that method convex hull, and it's going to take a list of points. Well, actually, this method getObjects, it returns a list of GUIDs of the object selected in the Rhino document. So we're going to get a list of IDs that correspond to the points. So let's call them point IDs. And the first step is to convert that list of IDs to a list of coordinates by using core 3D point. If you use core 3D point list, you can just do that for the entire list. So now you have a list of coordinates. So let's initialize an empty list to represent our hull polygon. So this list will contain all the vertices of the hull. So next we will start iterating through the list of points. Oh wait, I forgot something. I forgot to sort this list based on the x coordinate. So I'll use the Python's built-in sorted function. And as the key for sorting, we're going to pass a lambda expression. So each element in that list is a vector of length 3, and we're sorting them based on the x coordinate, which is the first member of the vector. So that will be our lambda expression. So that sorted list is going to be stored back into the points list again. So now that our list is sorted, we are ready to start iterating through them. So before we do that, so if you remember when I was explaining the algorithm, we first start at the beginning of the list and go all the way to the end, but we don't stop there. We work our way backwards from the end of the list back to the beginning. So in order to do all of that in a single loop, to keep the code cleaner, let's just create a list of indices that goes from the beginning to the end and back to the beginning again. So that will be a list ranging from 0 to the number of points to avoid counting the size of the list. Again and again, I'm going to put it in a variable because the list is not going to change in size. So I'm going to call it point count, pt count. So that's the list of indices from the beginning to the end. But we want to continue from there and work our way backwards to the beginning of the list again. So that will be a list ranging from the end of the list all the way to 0, which is -1 not included, and the step value will be -1. So that will give us a list. If the list of points is 10 long, the indices list will be a list of numbers from 0 to 9, and then 8, 7, 6, 5, 4, so on till 0 again. So we start iterating through the list of indices, and the current point in the list, let's put that in a variable and call it cur pt, representing the current point. So we said that if our polygon already contains a point, we don't want to process it. And our polygon is stored inside this hull list. So what we do is if current point in hull, forgot a space there. Okay, continue. We don't want to process that point. If it's a new point, if it's a valid point, then we want to add it to the list, but we want to do it safely. We want to make sure that it's a right turn every time. So how are we going to decide whether a turn between two edges is a right turn or not? So to make that decision, let's write a different method. Call it isValidTurn. It's going to take a list of points again. So to define a turn, you need 2 edges or 3 points. So that's what this list is. That's a list of 3 points. So let's make sure that the size of the list is always 3. That line will throw an exception if it's not. Then, well, let's get the vector representing the first edge. Which will be from the first point to the second point. I'm going to just copy that line to get a vector representing the second edge, which will be from the second point to the third point. And if the turn from V1 to V2, if it's a right-hand turn, then the cross product of V2 and V1 will be pointing upwards because cross products use right-hand rule. So we just calculate the cross product. And the cross product is pointing upwards if its z component is greater than 0. And if it's pointing upwards, then it's a right turn, which means it's a valid turn. So this method will tell us whether a turn is a right turn or not. Now, we have to check, when adding a point, we have to check whether adding that point, we have to check and make sure that adding that point to our polygon does not result in a left turn. So let's write a separate method that can safely add a new point to our polygon. Let's call it safe_extend. So we will pass a polygon, which is a list of vertices, and a new point. So first we'll go ahead and add the new point to the polygon. And we want to make sure that the last 2 edges represent a right turn. So first let's be sure that the polygon is more than 2 vertices long. So if its length is more than 2, then we can pass the last 3 points to this valid turn method, which will tell us if it's a right turn or not. So if it's not a right turn, I'm going to pass the last 3 vertices of our polygon using list indexing. Sorry, I meant to say list slicing, not indexing. So that is the list of last 3 points. So if our polygon has more than 2 vertices and if the last 3 points don't represent a right turn, then we delete the point at which the turn is happening, which is the second last point. But we don't want to do this just once. We want to keep checking it and keep doing this. So we will put this in a while loop. So yeah, this function should safely extend our polygon by adding that new point and making sure that it doesn't result in a left turn. So let's return the updated polygon. Now back to our main method. This is the main algorithm. We want to safely extend the hull with the current point. And yeah, that should do it. We loop through all these indices, which means we go from the first point to the last point and then back to the first point again. And there's one more thing though. So this condition is checking that, checking to see if that point is already in the polygon. So this means that our polygon will not be closed, because when we go from the beginning to the end and work our way back to index 0, the 0th point, the first point in the list, is already in the polygon, so it will be skipped. So we will have to add that manually outside the loop. To close our polygon. And we return the hull we've calculated. So let's just use the method in our main logic. And let's add a polyline, which would allow us to see the calculated hull. Okay, so that's the algorithm. I'm sure there's a bunch of bugs because I just typed it out. But yeah, we'll go through them and fix them. So select points. I selected the points. Okay, so points IDs in line 17. Yep, that's a typo. Yep, it worked. So that's the convex hull for that set of points. I'm just gonna add another point to the list and test it again. So I added that point. So now the convex hull should go through that point as well, because it's outside the previous convex hull. Yep, so seems to be working. Now, if the earlier explanation that I gave for the algorithm, if it was not clear, what I'll do is I'll just modify this algorithm just a little bit so that to make the algorithm show us what it's doing by visualizing the polylines before it's finished. So I'm going to create an empty variable here, and If it's not empty, we delete it. And we create a polyline depicting the hull that we've calculated so far in the loop. And we pause for a second. I guess I have to import time first. So I'll pause for 1/10 of a second. That should be enough. Okay. Oops. Oh, okay. It's unable to add the polyline to the document because at the beginning it doesn't have enough points. So let's do if length of hull is greater than 1. So now it only tries to add the polyline if it has at least 2 points. So you can actually see what it's doing. It's adding the points and then removing them. Okay, that was the last step before the final answer. Wait, let's just remove that last step as well. And I'll increase the pause to 1/5 of a second. Okay, now you should be able to clearly see how it progresses through the list, adding and removing points until it ends up with the final polygon. Oops. Okay, yeah. Rhino does that sometimes if you don't do the enable redraw thing. Oops. What happened to the... Okay, so the Python editor seems to be not working properly, but yeah, you get the idea. I hope the explanation of the algorithm was clear, and I'll post a link to the script that I wrote just now in the video description. I hope this was useful. Thanks for watching. Bye.